right, welcome everyone to our Ocean Model Working Group session this afternoon. Let me just, before we get started, remind you to remember the UCAR Code of Conduct, consider new ideas, encourage innovation, offer constructive feedback, acknowledge teamwork, show appreciation, and share the air. The usual, and I'll thank you in advance for doing that. So our first speaker this afternoon is Ting-Ting Zhu, talking about evolving Southern Ocean overturning in warming climates.
Thanks for having me. My name is Ting-Ting Zhu from UC Riverside. My advisor is Professor Wei Liu. Today I'm going to talk about evolving Southern Ocean overturnings in warming climates. The westerly wind stress can drive equatorial equipment transport, which can generate the Euro-rearming smog, also called Deacon cell or wind-driven overturning circulation. This overturning circulation is characterized by equatorial flow at surface and the polar and the upwelling of the deep water. The upwelling of deep water can steepen the aspinal slope. The baroclinic instability can flatten the aspinal slope and generate the eddies eddy-induced overturning circulation, which counteract the Euro-rearming smog. The eddies-induced smog act to compensate for the Euro-rearming smog, regulating the residual overturning circulation. Therefore, the Southern Ocean overturning circulation is a residual result of these two opposing overturning circulation. The eddy-induced smog can partially compensate for changes in the Euro-rearming smog induced by shift in zonal wind stress in the southern hemisphere. However, the degree of compensation is uncertain and influenced by surface buoyancy. In future climate warming with changing wind and changing buoyancy, the eddy-induced and the Euro-rearming smog response and the complex interactions and compensation between them are still uncertain under future climate scenarios. These uncertainties limit our ability to predict Southern Ocean's contributions to climate change, highlighting the need for further investigation. The Southern Ocean smog has changed in recent decades. Here we use ECHO dataset from 1992 to 2017. The figure shows the zonal mean westerly wind stress trend shows red color, and its climatology shows black color. As you can see, the westerly wind stress has a polar shift and intensification trend. This trend also can see from its spatial map. Associated, the Euro-rearming smog also trend with a dipole pattern with an intensification trend in the south and a weakening trend in the north, indicating a polar shift and intensification trend. The eddy-induced smog has an intensified trend which can provide partial compensation for the Euro-rearming smog. As a result, the residual smog mainly reflects the trend of the Euro-rearming smog. Besides changing wind, we also can see the buoyancy forcing has changed, which can contribute to the Southern Ocean smog dynamics. In brief, a polar shift and intensification trend has been observed in the Euro-rearming smog, while the intensified eddy-induced smog provides a small compensating effect. To see whether this trend will happen in future climates, we further investigate the Southern Ocean smog response in past and future warming climates using CME 5 and CME 6. For future warming climates, we focus on SSP 5.5's high emission scenarios compared to historical. And besides, we also focus on the past warming climates, implying warming period, which can be considered as an analog for future climate projections. For future warming climates, here shows the zonal mean westerly wind stress. In SSP 5.5 shows red color, and in historical shows blue color, and the difference shows black color. You can see the westerly wind stress shift polar and intensified, same as what we observed in recent decades. Correspondingly, the Euro-rearming smog also trend has a dipole pattern with an intensification in the south and a weakening center in the north, indicating a polar shift and intensification. The eddy-induced smog has a complex pattern, has a tripolar pattern with a strong weakening center, which can provide strong compensation for the uranium smog. Because of this strong compensation, the residual smog shows a uniform intensification. In the past warming climate, we also can see the westerly wind stress shift polar, but the westerly wind stress weaken a little bit, which is different from what we see in the future climate. Correspondingly, the uranium smog also shifts polar with a strong weakening center due to the weakened in westerly wind stress. The eddy-induced smog provide a weak compensation. As a result, the residual smog shows a non-uniform intensification because of the weak compensation from eddy, which is different from the future warming climates. In the future warming climate, the uranium smog undergoes a polar shift with strong eddy compensation, sustaining a uniformly intensified residual overturning. The polar shifting has been confirmed in the past warming, but with weaker eddy compensation leading to a non-uniform intensified residual overturning. Besides changing wind, we also investigate how changes in buoyancy forcing affect the Southern Ocean overturning circulation. Because the eddy-induced overturning circulation is proportional to the isopinal slope, so we further analyze the isopinal slope change in both future and past warming climates. As you can see, there's flattened isopinal slope in both future and past warming climates, which can explain why there's weakened eddy-induced smog. The flattened isopinal slope is caused by the change density flux. The top right panel shows the total density flux, which comprises the density flux due to the heat flux turn and due to the freshwater flux turn. Can see compared to historical, there's a decreased density flux in future warming climates, and this decreased density flux is mainly due to the heat flux turn with a small contribution from the freshwater flux. Same story happened in past warming climates. Therefore, the weakened eddy-induced smog in both future and past warming climates is driven by a flattened isopinal slope primarily caused by increased surface heat flux. Associated with the buoyancy forcing change, the water mass formation also changed in the past and future warming climates. This figure shows the area for surface density in SSB 55 shows red color, in historical shows blue color, and the difference show as black color. So compared to historical, there's a lighter surface density in future warming climates. If we look at water mass transformation, both historical and SSB 55, there's a lightening transformation, but the lightening transformation shifts northward in future warming climates. When water accumulates in a certain density of decrease in a certain density, the imbalance should be resolved by the downwelling of outwelling. Because, for example, because there's lightening transformation, water in a lighter density will accumulate, which can drive downwelling. Because the lightening transformation shifts northward in future warming climates, the downwelling and outwelling also has been shifted northward. As a result, compared to historical, you can see there's a downwelling and outwelling on the both sides of around 50 degrees south, which is related to the weakened eddy-induced smog, as we mentioned earlier. And besides, around the Antarctica, there's a downwelling anomaly, which support the bottom water mass formation in the Ross Sea and Weddell Sea. Similarly, in the past warming climates, we also can see the lightening transformation shift northward, but it has larger displacements, as well as the outwelling and downwelling has larger displacement. The associated buoyancy forcing changes have driven northward outwelling around the Antarctica with larger displacement over the past warm period, promoting the bottom water formation in the Ross and the Weddell Sea. Associated with the overturning circulation change, the response of Southern Ocean ventilation also changed. The ventilation can be measured by the ideal edge, which represents the average time since the water last resided in the surface layer. In both future and past warming climates, we can see there's enhanced ventilation in the subduction branch. This enhanced ventilation is caused by the intensified overturning circulation and thereby the enhance the subduction branch. Compared to the future warming climates, the subduction is enhanced and deeper and widespread in past warming climates. This characteristic also can see from each different models, especially from IPSL simulation. Therefore, along with overturning circulation trend, the ventilation intensifies in the subduction branch, especially during the past warm period. In conclusions, first, under high emission scenarios, the uranium mode shifts polar with strong eddy compensation sustaining a uniform residual overturning. In the mid-Pliocene, a similar shift occurs, but weaker eddy compensation leads to an uniform residual response. The associated buoyancy forcing trend have driven up northward upwelling around the Antarctica with larger displacement over the past warm period, promoting the bottom water formation in the Ross and the Weddell Sea. Alongside trends in the Southern Ocean overturning circulation, the ventilation linked to the subduction branch intensifies, particularly during the past warm period. This intensified ventilation has critical implications for climate feedbacks, impact ocean heat uptake, carbon storage, and air-sea interactions. That's all about my research. Thanks for attention.
Questions, come up to the mic, please. List here in your last point, critical implications for climate feedbacks, et cetera. I wonder if you could speculate on what some of those might be.
This slide?
No, just the very last slide with your 3 points on it.
Oh, last slide.
The conclusions.
Oh,
yeah,
conclusion, sorry.
Yeah, we were just on it.
Oh, it's out.
Is it gone now?
Yeah.
Oh, we're back. Yeah, just here. So, critical implications. I wonder if you could speculate on what some of those critical implications might be.
You mean the climate feedbacks?
Yeah, any of them.
Oh, I see. Yes. I think the enhanced. Sorry. I think the enhanced ventilation, that's the ocean can uptake more heat, heating from the atmosphere, so they can, I think, can modulate the global warming. Yeah, that's one part.
Can you go to your conclusion slides, please?
What? Oh, conclusion.
The first point is there's the shift in the wind.
Yeah.
And then you say that enhances the buoyancy forcing around Antarctica. But none of these models, so if you have polar shift on the wind, you have more warm water going towards Antarctica. And none of these models have an active ice shelf or ice sheet model couple. If they were, then you would have extra buoyancy forcing around Antarctica. You think that would change your second bullet point?
Mm-hmm. Can you explain a little bit?
Like, none of these models have an active ice sheet. So they're missing, if you were to drive more heat towards Antarctica with an ice sheet model, you would increase the melting. And then you would put more fresh water around Antarctica.
Yeah.
But these models don't have that.
Oh, I see.
We can talk offline again.
Yeah, sure. Thank you.
about evaluating Southern Ocean heat uptake.
Good afternoon. First of all, I would like to thank NCAR for having me here. My name is Anthony Thomas. I'm a third-year graduate student at the University of California, Riverside. Today I will be talking about evaluating Southern Ocean heat uptake in high-end low-resolution climate models, with specific emphasis on the HARGEM 3GC 3.1 and CESM 1.3 models. This project was done in collaboration with my PhD advisor, Professor Wei Liu. Okay, I would like to start with a brief introduction on why I was focusing on the Southern Ocean. So we know that in the recent decades, the Southern Ocean is going through a lot of changes. It includes the warming within and as well as north of the Atlantic circumpolar current. We also seen the Southern Ocean is getting warmed all through up to upper 2,000 meters as well. In addition, we're also seeing the Southern Ocean is showing trends of freshening south of 45 degrees south, and it is also extending into the ocean interior as well. In addition, we are also seeing increase in the zonal wind stress in the southern hemisphere, which represents intensification of the westerly winds in the Southern Ocean. And in response to that, there was an increase in the eddy-kinetic energy in the Southern Ocean. So which means that it's really important to have the mesoscale eddies resolved in the ocean models while we are dealing with the Southern Ocean dynamics. And it was found that the explicitly resolved mesoscale eddies reduce subsurface ocean model warming drift, improving the realism of water masses relative to those in the Stratton models. And a study by Hewitt et al. 2017, they mentioned that the accurate simulation of climate change responses in the Southern Ocean was reported to be critically dependent on the mesoscale eddies. So that's kind of the motivation for our study, that we are trying to compare a very high resolution ocean model from the HIROS MIP and compare it with the low resolution model, and compare both of this with an observation benchmark, and to see how well the resolution increase in the horizontal resolution is helping in understanding the Southern Ocean dynamics. So for the assay observational benchmark, we are using 3 observational based datasets, which are the Ishii et al., IAP, and EN 4.2.2. We are analyzing from the period 1958 to 2014 within the region of 30 degrees south to 70 degrees south in the upper 0 to 1,800 meters. And all the observational data are interpolated to Ishii vertical levels for consistency. Moving on to the climate models, we are using 2 different high-resolution models. One is the HARGEM 3GC 3.1 from the UK Met Office, and the other one is the CESM 1.3 by the IAS program. Both of them are participating in the HIROS MIP protocol, and we are using 2 different simulations, the historical 1950 and also the control 1950. We are doing a drift correction using by removing the linear trend of the control 1950 from the historical 1950. Looking in detail about these 2 climate models, we have 2 resolutions. We have the low resolution ocean, which is at the standard nominal resolution, that's at 1 degree, and we have the high resolution that's at 0.1 degree, and that's the same for HARGEM and as well as the CESM model. So in order to separate the temperature trends, we are using this heave and spiciness decomposition method, where we are decomposing the total temperature into the temperature changes associated with the heave and the spiciness. So heave is associated with the temperature change that is caused by the vertical movement of the isopycnal layers, and the spiciness is associated with the changes along the isopycnals. So basically, the heave is mostly correspondent to the changes that are influenced by the zonal wind stress or surface wind forcing changes, and the spice or the changes along the isopycnals are majorly driven by changes in the surface heat fluxes. So moving on to the results, this is at first I'm showing the ensemble mean of observations that's in the panel A, and in panel B and C that's the HARGEM model, the high resolution and low resolution versions of the HARGEM model. So first of all, if you're looking into the observations, we can see that the observational-based datasets are consistently showing a cooling south of south of 55 degrees south in the upper 100 to 200 meters, and also to the north of 55 degrees south, the observations are showing a warm tongue that is extending equatorward. When comparing it with the Harjum model, both the high resolution and low resolution versions are failing to reproduce that cooling that we are seeing in the southern part of Southern Ocean. But then the high resolution version is producing a deeper and stronger warming north of the 55 degrees south. And we just did, so like I mentioned, I did decomposition of this total temperature trend into the spiciness and heave components. We then looked into how the heave and spiciness trends are changing in the observations and the Harjum model at first. So here the central panel depicts the spiciness trend, and the bottom panel depicts the heave associated trends. So what you can see here is that in the observations, the surface cooling south of 55 degrees south is mainly driven by a negative spiciness trends, and the subsurface warming north of 50 degrees south is arising from the heave associated positive contribution. And when you're comparing it with the Harjum model, especially the high and low resolution models, and specifically looking to the south of 55 degrees south, both of the models are in the spiciness trends, both of the models are showing warming instead of the cooling that we have seen in the observations. And to the north of the 50 degrees south, the warming tongue is associated with the heave component, similar to that of the observations. But then the deepening of the heave component is, the high resolution model is showing more stronger and deeper heave, which is more closer to the observations. We also parallelly checked the CESM 1.3 model, both the high resolution and the low resolution versions. And this figure is similar to the figure 1, where I'm showing the total trend of CESM high resolution and low resolution with the observations. So here again, both the CESM 1.3 resolutions are failing to capture the observed surface cooling south of 55 degrees south. And they're also underestimating the warming north of 55 degrees south in both resolutions when we are comparing with the observational mean. And the high resolution version is showing a deeper warming tongue, but with a weaker magnitude than the high resolution and the low resolution, than the low resolution and the observations. We also did we then looked into the spiciness and heave decomposition for the CESM model, and similar to Harjum model, the CESM high resolution and low resolution are showing warming to the south of 55 degrees south in terms of the spiciness. And to the heave, we are seeing an increase, the heave component, similar to the Harjum model, that's the major contributor for the deepening of the warm tongue. But then it's comparably weaker and shallower when compared to the observations. So given that there is a difference between the resolution-dependent spatial variations of the heave and spiciness and as well as the total temperature trends, we now look into the physical mechanisms that might be causing these changes. Specifically, we start with the Harjum model. So from this point onwards, what I'm showing is the anomalies with respect to the 1950 control. And here, so the panel A is the net surface heat flux anomalies, with the red line representing the Harjum high resolution model and blue line representing the low resolution model. And in panel B, that's the decomposition of the net heat flux into net turbulent and net radiative, with the purple line representing net turbulent and green line representing net radiative fluxes. So jumping quickly into the key conclusions from this slide, when I'm looking into the Harjum high resolution models, it's showing a net surface heat flux anomalies, positive net heat flux anomalies from 70 degrees south to 35 degrees south. And these positive anomalies are largely due to the enhanced turbulent fluxes, especially the latent and sensible, especially the south of 60 degrees south. And this explains the positive spiciness trend and the absence of observed surface cooling in the high resolution simulation. And to the north of 60 degrees south, there's a continued positive net heat flux, which is driven by the turbulent and radiative contributions. It's aligning with the approaching warming in the spiciness. Looking into the Harjum low resolution version, it shows a weaker net heat flux anomaly south of 64 degrees south compared to the high resolution. And this is because the positive radiative fluxes are being offset by stronger negative turbulent fluxes, leading to weaker surface warming and the spiciness trends south of 64 south. So from 64 degrees south to 45 degrees south, there's an increase in the net heat flux which is peaking around 57 degrees south, and again, due to the turbulent flux changes. In parallel, we check the surface flux anomalies in the CSM model. So looking into the high resolution version, it's showing a positive net heat flux from 68 degrees south to 47 degrees south, and peaking at around 58 degrees south. And here in CSM high resolution, the radiative fluxes are dominating south of 61 degrees south, and to the north of 61 degrees south, it's the turbulent fluxes that are dominating. Whereas in the CSM 1.3 low resolution, the positive net heat flux from the 70 south to 30 south is peak. We are seeing a positive net heat flux from 70 south to 30 south, which is almost peaking around 56 degrees south, again, driven by turbulent flux changes. And south of 60 degrees south, the positive radiative flux nearly getting cancelled by the negative turbulent fluxes. So the key takeaway from this slide, and if I'm connecting it back to the other slides, is that when we're looking into the surface, the Southern Ocean, we can see like in both the high resolution and low resolution versions of the CSM, both HRGM and the CSM, we're seeing a surface warming, and this is kind of like due to the changes in the spiciness component. And when even there are, and it's not uniform actually. There are localized changes in this warming trends, and when we are looking into these surface flux changes, we could see that these surface flux changes are basically aligning with those changes in the spiciness components. And they also are showing these localized changes. So that explains the spice port, and then we looked into the heave-induced warming to the north of 50 degrees south. So for that, as I mentioned before, the heave component is mainly driven by the changes in the zonal winds. So we looked into the zonal wind changes. Again, it's anomalies respective to with respect to the 1950 control. And so here in panel A, that's the zonal wind stress anomaly with red line representing the HRGM high resolution and blue representing the low resolution, and the control is in the background. Panel B is the wind stress curl anomalies with the red representing the high resolution and blue representing the low resolution. And C and D are the spatial patterns of the zonal wind stress anomalies in the high resolution and low resolution. So quickly jumping into the main conclusions from this slide. When you're looking into the high resolution models, the zonal wind stress anomalies are showing a positive, it's showing a dipole which is nearly centered around 42 degrees south, with a positive to the south and a negative to the north. And this indicates the poleward intensification of westerlies. And similarly, in the low resolution, we could also see the same dipole pattern, but now in the in the low resolution version, the dipole center is further south, almost like around 46 south, and then the positive is to the south and negative is to the north. When you're looking into the wind stress curl, the positive anomalies in the high resolution are starting from almost, we are seeing positive anomalies to the north of 55 degrees south, which is almost peaking at around 46 degrees south. And then there is the negative curl anomalies south of the 55 degrees south. And in the low resolution, we're also seeing these positive anomalies, but then the positive anomalies are beginning at almost around 58 degrees south. And then it's peaking around like 48 degrees south. And then we have the negative anomalies to the poleward. So, so together with the poleward intensification of the westerlies and the positive wind stress curl anomalies, it is inducing a Ekman convergence, and which leads to the deepening of the isopecular in this region that represents the deepening of the heave-induced warming in the Southern Ocean, especially in the HRGM model. We didn't got the data for the CSM to show here, so I'll just quickly jump to the conclusion here. So these are the conclusions from my study. We are seeing subsurface warming patterns. Example, the warming tongue north of 55 degrees south. Both the resolutions are capturing, but then the high resolution versions are reproducing the deeper warming tongues due to stronger heave contributions associated with positive wind stress curl anomalies. Surface cooling south of 55 degrees south is absent in all models, and it all simulates spiciness-driven surface warming instead of cooling. And this is linked to the underestimated sea ice expansion in the climate models, causing excess surface heat uptake in the region south of 55 degrees south. And turbulent heat fluxes acts as the main driver of spiciness-induced surface warming, and radiative fluxes play a contributing role. So in general, each of the resolution has its own positives and negatives, and when each resolution is showing a regions and process-specific strength and limitations. That leads to the highlight that we need to, there's a need to be improved, the need for improved surface turbulent flux simulations, CS dynamics, and wind forcing in the climate models to represent much more accurate Southern Ocean dynamics. With that, I will conclude, and thank you.
Any questions? Very nice talk.
Yeah.
So do you have any hypotheses as to why none of these models get the surface cooling south of 55?
So, all right, okay. So I just looked into the sea ice concentration, and when you're comparing it with the HADA SST, so I use a HADA SST as an observation benchmark, and in the recent decades, almost like after 1990, the CS variability is showing positive trends in the observations, whereas in the models, they're not capturing that CS variability. So probably due to the decline of sea ice or the variation in the sea ice in the models, there could be more open ocean available, and then more surface heat fluxes coming into the region south of 55 degrees south, which might be the reason for that warming to the region south of 55 degrees south in the models compared to the observations.
You are looking at the high-res MIP simulations, right? So if you look at the actual historical simulations that we have done under the Mesa Clip or IHAS project, which are available, we have 10 members, you'll see that at least 3 or 4 of them will get the Southern Ocean cooling.
Okay.
I don't think that high-res MIP is the right framework to look at this because it has other issues with the TOAs and all that stuff.
Okay.
Yeah.
Thank you for the insight.
All right, thank you again, Anthony. I think we're going to move on to the next speaker.
Yeah. And how do I point?
Yep. We got it. Okay. It's Rudra. Yeah.
You can call me Rudra.
Rudra.
Yeah.
Tucker. All right. All right. Next speaker is Rudra Tucker from Wisconsin-Madison. All right. Go ahead.
So good afternoon, everyone. My name is Rudra Thakur. I'm a PhD student at the University of Wisconsin-Madison in the Department of Atmospheric and Oceanic Sciences. And now we'll be shifting gears to North Atlantic region, and I'll be talking about Northwest Atlantic marine heat waves and whether we need high-resolution models to simulate those events. I would like to thank all of my collaborators and also the Ocean Model Working Group, and especially my advisor, Professor Elizabeth Maroon, for all the support and just being amazing. So what are marine heat waves? Marine heat waves are periods when ocean temperatures stay unusually high, particularly above a certain threshold, and then extend for time. In this talk, I'll focus more on the Northwest Atlantic region for marine heat waves, and this region is especially important because the warming is nearly 4 times faster than the global ocean average in this particular region. It is also shaped by dynamic ocean currents like Gulf Stream presence, which makes it really interesting to study. So 2 most widely studied marine heat waves in Northwest Atlantic occurred in 2012 and 2016. These events stood out because they had unprecedented warming, they had record-breaking warming during those years, and also had significant impacts on marine ecosystem. Both these events were triggered by poleward shift in jet stream, which caused positive anomalous heat fluxes into the ocean, which initiated SST anomalies. And then the ocean advective processes kind of amplified and sustained those anomalies for summer and fall in these different events. This also highlights that there are multiple processes, both atmospheric and oceanic, that shape the life cycle of marine heat waves. And so the ability of the climate models to simulate these events depend on how well they capture these key mechanisms, and that will be the focus. This brings to our question. So how and why do marine heat waves differ in eddy resolving and non-eddy resolving ocean models in Northwest Atlantic region? The impact of model resolution in Northwest Atlantic region is not a new idea. Previous research has shown that model resolution affects mean state biases. And a quick shout out to Ping Cheng's great talk on this yesterday where he highlighted IHESP's improvisations. So here's an example from Zhu et al. 2022, which shows that the Gulf of Maine, which is in the white box, tends to be colder and fresher in high resolution. Colder and fresher in high resolution models as compared to the low resolution ones. This is likely due to a more poleward extension and then detachment of the Gulf Stream in low-res models as compared to high-res, which affects the water mass placements, temperature, salinity, and also impacts stratification in the ocean. So if model resolution affects the background ocean state, how does that translate to marine heat wave behavior? And to understand how biases between high-res and low-res models affect marine heat waves representation when both are forced by the same atmosphere, we use the Community Earth System Model Forced Ocean Sea Ice Simulations, or FOSSEs. So FOSSE consists of simulations where both low-res and high-res models are driven by the same atmospheric forcing from JR 55. The low-resolution version has a 1-degree ocean model resolution, and all the parameterizations are turned on. In contrast, the high-resolution model is 1/10 of a degree, and all the key parameterizations like Gent-McWilliams and Fox-Camper are turned off because they explicitly resolve those eddies. Since the ocean heat budget closes in FOSSEs, these simulations are ideal for diagnosing the mechanisms behind observed marine heat waves, and yet they have been underused for this purpose. To evaluate how well the models perform, we'll compare them with some observational benchmarks like OI SST for sea surface temperature and EN4 objective analysis for subsurface conditions. So moving on to some results. Let's look at how these two model versions compare in their mean state climatology. The shading in this figure shows salinity averaged over the upper 110 meters from 1983 to 2018. And the red and the orange contour lines represent the 15 degrees Celsius and 4.5 degrees Celsius isotherms, respectively. So when we compare the model climatologists to EN4, we see that the low-res FOSSE has warmer and saltier Gulf of Maine, which is again in the white box, as compared to both EN4 and high-res models. And no surprise here, but high-res does better job and is well comparable to the observations. These temperature and salinity biases in the mean state are important because they kind of help set the background conditions for marine heat waves. And from this point on, all of my figures will be highlighting for that white box. So all of the line plots are for Gulf of Maine, not the entire Northwest Atlantic region. So let's revisit the two marine heat waves that we discussed earlier. The top row now shows the absolute sea surface temperatures from high-res FOSSE, low-res FOSSE, and OI SST for the 2011-12 event and the 2015-16 event. Consistent with the mean state bias, low-res FOSSE is significantly warmer in Gulf of Maine and almost 5 degrees above observations during both the events. And in contrast, you can see high-res FOSSE captures SST much closer to the observations. Since marine heat waves, however, are typically studied using anomalies, the bottom row shows the SST anomalies for the same events, and this is where it gets interesting. So for 2011 and 12 event, the high-res FOSSE actually closely matches the observed SST anomalies, while low-res FOSSE underestimates the marine heat wave. However, during the 2015 and 2016 event, neither model clearly outperforms the other, and both have discrepancies when compared with OSST anomalies. In the interest of time, I'll focus on just the 2015-16 marine heat wave. And although neither model better represents the observed SST anomalies, this simulation still allows us to explore how the event evolved, and more importantly, how the underlying processes compare between the models. This gives us a way to assess whether the mechanisms driving these marine heat waves are being realistically captured or not. To understand what's driving these marine heat waves, we perform a heat budget decomposition integrated over the upper 110 meters of the ocean to account for the mixed layer dynamics. And anomalies are calculated relative to 1983 to 2014 climatology. And the breakdown is pretty straightforward. The total temperature tendency just equals the sum of contributions from surface turbulent heat fluxes, radiative heat fluxes, total resolved advection, and then subgrid scale processes. However, it is important to note that subgrid scale processes here are two different things because the two models have two different parameterizations. So in low-res FOSSE, all parameterizations are active, so this term is largely governed by KPP, diffusion, Gent-McWilliams parameterization, and Fox-Camper parameterizations. Whereas in high res, because eddies are explicitly evolved and represented, only KPP and diffusion play a role in that particular term. And a huge shout out to Annalena Teppenmeyer to help me with the heat budget decomposition. So to some results again, the figure here shows the total temperature tendency on y-axis and the time on x-axis, and both low-res FOSSI and high-res FOSSI exhibit positive tendencies during winter that initiated the marine heat wave and sustained over the summer. In fall, the high-resolution model shows an increase in the intensity of the marine heat wave. That's the mountain-like peak in the fall, aligning with the observations at this time, and something that the low-res model completely misses out and does not capture. So now to understand what drives this temperature tendency, we can now do the heat budget breakdown. The red line here shows the turbulent and radiative heat fluxes overlaid on the total temperature tendencies, and it's clear that the initial ocean warming in winter is almost mostly driven by changes in turbulent and radiative heat fluxes in both high-res and low-res. Further investigation shows that these are largely driven by the turbulent heat fluxes, and that makes sense that because this event was caused by the polar shift in jet stream, there should be more anomalous heat fluxes into the ocean, and both the models actually kind of show that. But interestingly, the low-resolution model shows stronger anomalous warming than the high-resolution one, raising the question why this difference occurs. And it's a very nuanced point, but I think it's important to show that and not just cause questions. So this schematic here shows the difference between low-res and high-res climatology and how it affects to these heat fluxes, and it goes back to the mean state biases. So because the mean state SST is higher in low-res, there is a larger reduction in turbulent heat flux out of the ocean for the same reduction in wind speed. So they're both forced by the same atmosphere. You just see there's a larger difference. And this means that the mean state biases directly impact the representation of marine heat waves in these models. It is also clear that turbulent heat fluxes alone do not explain the full evolution of the marine heat wave, especially the fall intensifying of the marine heat wave. And it is actually showed by the resolved advection in the high-res over fall. So based on observations, a study was published by Perez et al. 2021, which kind of finds that this particular fall anomalous warming was caused because of warm core eddies present in that region. And that makes me believe that this advection could be coming from the eddies. And that would also explain that why the low-res is not showing any resolved advection patterns, because these eddies are kind of lumped into the subgrid scale parameterizations rather than explicitly resolved. So do the subgrid scale processes in the low-res model show similar patterns in advection when we look at the subgrid scale parameterization? And the answer is no. So parameterized eddies have minimal effect in marine heat wave intensification in low-res FOSSIs. We can examine the spatial patterns of total advective tendencies in both the models. So in the low-resolution model, we see kind of a dipole emerging in the Gulf of Maine, which nearly cancels out, resulting into an almost neutral net advection effect. Whereas in contrast, the high-resolution model exhibits strong positive advective anomalies in Gulf of Maine, especially in the coastal regions and also at the southeastern Gulf of Maine region. To isolate the eddy contributions, we separate the eddy advection from the total advection in both the models. And now the low-res model still shows an opposite sign dipole, so it's flipped from the total advection, but it still kind of cancels out, and there is not much advection or any warming tendencies emerging out of it. Whereas in the high-res, it's clear that most of the total advection is driven by those eddies. And I don't have that updated figure because of the NCAR maintenance, but that southeastern anomaly that you see, when you zoom out of that region, it's actually coming from an eddy that was shed off from the Gulf Stream meanders. So it highlighted that how Gulf Stream, or representation of Gulf Stream, might also be influencing this marine heat wave representations in FOSSIs. This kind of brings me to the summary. So CESM FOSSIs are great tools. Go use them to understand marine heat wave evolution from heat budget analysis perspective. High-res FOSSI better captures the mean state water masses, resulting in more realistic marine heat wave simulations. The mean state biases in low-res, and particularly coming from the higher SSTs, lead to larger anomalous turbulent heat fluxes during the 2015-16 marine heat wave or winter. And then resolving these mesoscale eddies improves the marine heat wave representation in the Gulf of Maine by capturing the Gulf Stream variations that could drive and intensify these events. And I'm not showing the 2011 and 12 event here, but both the cases kind of show that the parameterization always has an opposite effect as to what the resolved eddies are doing, and that's one of the key takeaways, that in this phases, it's not that they're trying to either have both positive anomalies or negative anomalies, they're always opposite of each other. Here are some references, and with that, I'll take questions. And shout out to Elizabeth Maroon for the podium.
Hi, nice talk. Thank you very much for that. Marine heat waves aside, I'm curious if you looked at just SST variability generally between the two simulations, like if you just did point-wise correlation of SST, if the high res has an advantage there. So that's a good question. Mean state and point-wise correlation, the Northwest Atlantic region in general, the high res is much better represented in low res. Globally, it's a different story. Globally, there are regions where it's warmer and colder, but high res still is better observing the SST anomalies and mean state SSTs. But I don't know about global, but Northwest Atlantic, yes, high res has a better representation. So have you looked at the variability? Sorry.
Not at the variability, no. Just like not interannual variability or decadal variability, no. Just
Thanks.
mean state. Thanks.
Okay, could you back your sixth slide?
Yeah.
I have a quick question. Do you think the results are caused by the geography, I mean the open of the channels instead of the resolution?
Yeah, so high res clearly has more resolved coastal representation, and also the bathymetry is also important. So one thing, we haven't looked into that yet, but I would assume that definitely resolving those coastal processes. I'm not sure how the runoffs are integrated in this model, but coastal processes definitely help in resolving that. Also, the Gulf of Maine has kind of a very interesting bathymetry where south of Gulf of Maine, there is actually a deeper region that shows up. And that region is small enough that it might not be resolved in low-res Fosse because it's 1 degree, but it is resolved in high-res Fosse. And that's the region where we also see that huge positive anomaly going in towards high-res. So yes, but I don't have a way to show it yet.
Thank you.
Thanks. Okay. Thanks.
Our next speaker is Tedra Lowe, that will talk about CSM, how CSM has more subpolar North Atlantic water mass transformation than other models. Please go ahead.
Hi, everyone. I am Tedra Lowe. I'm a grad student at the University of Wisconsin. I'm working with Elizabeth Maroon, just like Rudra. I'd also like to thank my collaborators, Stephen Yeager and Feng Zhu as well, for all of their help. So to begin, I'm sorry, just a warning, if you can't see some of the lines on my plots, all of my stuff's on Scratch, so I wasn't able to access the things that I wanted to, but I'll try my best. So I'll start by introducing water mass transformation, which we've heard about a little bit throughout the talks. Basically, water mass transformation is the amount of seawater transforming from one density to another. And those density changes occur through buoyancy forcing, and through the Walling framework, we're able to relate overturning circulation to water mass transformation. Oh, and here's a schematic showing that. And water mass transformation can be broken down into two different parts. We've got water mass transformation at the surface from heat and freshwater fluxes. We've got water mass transformation also from mixing, and that's due to internal processes. But in the subpolar North Atlantic, we've got these outcropping isopycnals at the surface, and so overturning circulation can largely be related to water mass transformation at the surface. So to calculate water mass transformation, we've got a density flux, and to get the density flux, we just use the surface heat and freshwater fluxes, and we sum up, so say we take these isopycnal outcrops, we just sum up the fluxes or the density flux over that range, and you're able to get a water mass transformation. And if water mass transformation is positive, that means we're moving towards heavier density classes, and if it's negative, that means we're moving towards lighter density classes. And I'd also like to highlight that I use the Python package XWMT. It's an awesome package. Jan-Erik Tesla works on it, Graham McGilchrist, and it also uses the TEOS 10 equation of state as well. So that brings us to the goal of my talk here, and that's to investigate the differences in subpolar North Atlantic overturning circulation between CESM2 and other FOSSI models like Rudra introduced before, and that participated in the OMIP simulations. And so the objective here will be to analyze water mass transformation and AMOC in the OMIP models. And as a reminder, OMIP1 is forced by CoreV2 forcing, and OMIP2 is forced by the JRA55DO forcing. So to compare the OMIP models, we wanted an observational benchmark to compare them against. And to do that, we constructed observation-based estimates of water mass transformation. And I used the ACOM set, which probably not a lot of you are familiar with because no one ever uses it. But it basically just couples data together. You take the model components out and you just replace them with data. And the cool thing about this is that I can use JRFD5DO forcing as well as the CoreV2 forcing, which is the same forcing as the OMIP models. So we can have a more direct comparison to these observational benchmarks to the OMIP models. And so basically I just hijacked the CESM coupler in the bulk formulae and I input these data sets, and to get a spread in the fluxes, I use different sea surface temperatures. So here I use HAT-ASST and OASST, and then for sea ice, I just use HAT-ASST sea ice, and then for runoff, we've got the JRFD5DO and the Dye-Trenberth. And so when we calculate the fluxes, here's an example of what that looks like. These are the surface heat fluxes. When we use the 2 different sea surface temperatures and the 2 different atmospheric forcings, we're able to get 4 different surface heat flux fields, and we only get 2 different freshwater flux fields because it's not really impacted by the sea surface temperature. And then we just input those into the density flux, and we're able to calculate water mass transformation. And to make sure that our data sets are self-consistent, we wanted to use the same sea surface temperature from the density field that was used for the surface fluxes. And so we've got the 2 different flux fields from HAT-ASST and then 2 different surface density fields from HAT-ASST matched with EN4 and ISHI. And if we do that same thing with OASST, we're left with 8 different observation-based water mass transformation benchmarks. And so here are the 8 benchmarks that I have computed. In the subpolar North Atlantic, we can see there's an obvious spread in the water mass transformation. And so to get a better feel of where this spread is occurring, I broke down the water mass transformation into these different areas here. And we can see that in the Nordic seas, there's definitely a large spread in the water mass transformation, as well in the subpolar gyre too, and that is what's contributing most to the spread in the subpolar North Atlantic water mass transformation. And the subpolar North Atlantic is just a sum of all of those regions. And so now, sorry, it's really hard to see the gray shading. But now if we compare the observational benchmarks, so any benchmark that uses CoreV2 forcing, because we're looking at OMIP1 models, it's hard to see, but let me see if I can use the pointer. There we go. There is the observational benchmarks. The subpolar North Atlantic water mass transformation from the OMIP1 models is shifted towards heavier density classes, and the majority of the water mass transformation is also a lot stronger than the observational benchmarks. And if we look at the different regions, we're able to figure out where this spread is coming from, and we can see in the subpolar gyre, the southeast region, there's a large spread in water mass transformation in the backs, and it's also shifted towards heavier density classes. If we're looking at the Erminger Icelandic and Nordic seas, we see a large spread in the density classes of the max, and it's also it's too strong compared to the observations. And then last, if we look at the Labrador Sea, we also have water mass transformation that is too strong in these models. And to point out CESM2 relative to the other models, you can see that CESM2 has some of the strongest water mass transformation compared to all the OMIP models and the observations. And again, we can see that comes from the Labrador Sea and the Erminger Icelandic seas. And then the same behavior occurs in OMIP2 as well. You can see the gray shading, the observational benchmarks. Here I'm just using the benchmarks that use the JR55 DO forcing. And again, we see the large spread in the subpolar gyre and shift towards heavier density classes, a large spread in the Irmingar Icelandic seas and Nordic seas, and too strong of water mass transformation in the Labrador Sea. And also, we still see that CESM2 has some of the strongest water mass transformation in the subpolar North Atlantic, again, attributed to these two regions. So if we're looking at the AMOC string function at 45 degrees north, you can also see that there is there's stronger transport in CESM2 compared to the OMIP2 models. And so that pink curve there. And I'd also like to mention that this data is processed by Liz and Steve, so thank you for that. And when we are looking at transformation maps, so transformation across, say, a specific density class, here I'm using 36.5, we can pinpoint locations of strong transformation. And so if we're just looking at CESM2, we can see compared to some other models that we've got strong transformation, water mass transformation in the Irmingar Icelandic seas, and it's hard to see here, but there is stronger water mass transformation in the Labrador seas. So the key takeaways of this talk is that most OMIP simulations have water mass transformation that falls outside the observational range. The maximum transformation generally occurs at heavier density classes than the observations imply. And we've got strong biased water mass transformation that we attribute to the Labrador and Irmingar Icelandic seas. And there is additional OMIP spread that comes from the southeast subpolar gyre. And lastly, CESM2 has some of the strongest water mass transformation and AMOC among the OMIP models, and that's because of the Labrador Sea and the Irmingar Sea. And that's it.
Questions?
When we look at OSNAP, we see like a strong seasonality in the bias, and I'm wondering if you have tried to look at seasonality in the water mass formation to see if that we can relate them essentially.
Yes, so I have looked at seasonality. Those plots are a little hard to understand, so I will definitely talk to you more about that after this, and I can show you those plots.
So, nice talk. How much do you trust those observations?
That's a good question. Yeah. I do think the JR55DO set is a little bit better than the Core V2. But I think for this instance, I wanted to use those data sets because I wanted to compare them to the models. And they're created to force the models. So I think it would definitely be better than using reanalysis data sets for this case. But yeah, it's hard to trust surface fluxes. It's rough. Yeah.
Any questions for Tadra? If not, let's thank her one more time. And our next speaker is Liz Maroon, and Liz will talk about process-oriented diagnostics of the subpolar North Atlantic for ocean and couple model development.
Hi, I'm Elizabeth Maroon, and I'm working with, I guess, the other, last half hour worth of folks. Thank you to the Ocean Model Working Group for giving my group so much time. I really appreciate it. You did not need to give me a talk after them. That's very kind of you. So this is going to be a little bit different of a talk. This is not going to be so much a science talk as a diagnostic talk. We don't often talk about how we diagnose our models during the development process, but that's really what this talk is about. So this is a project that Steve Yeager and I have to put together process-oriented diagnostics for the NOAA Model Diagnostics Task Force package. And Tadra talked about a lot more of the science aspects of this. This is going to be kind of a mock-up of what our deliverable is going to be looked like for getting into that package, as well as we hope into Cupid. So there's been a lot of contributions. You just heard from Tadra. You'll see some similar plots on this. But here at NCAR, we've had contributions from Brendan Myers, Feng Zhu, Dylan Oldenburg, and Tegan King. So this has been much a team project. So the problem is that climate models have struggled with sea surface temperature and salinity fields in this northwest corner region since basically flux correction ended. So when we let the ocean and atmosphere talk to each other, you get big biases in the Gulf Stream and North Atlantic Current, and this leads to what's been dubbed in this very colorfully, the blue spot of death. And you can see it in CMIP 3, you can see it in CMIP 5, you can see it in CMIP 6. So why does this occur? It's because they're getting the Gulf Stream and the North Atlantic Current in just the wrong places. So I've got the upper ocean 200-meter temperature bias here on left. Let's see, can I point? Yeah, cool. Up on the left, and then here's the upper ocean salinity bias on the right. In the gray contours are the climatological fields from EN4, and so you can kind of imagine for the isotherms, that's where the Gulf Stream and North Atlantic Current is. So the reason we call this the northwest corner is because you've got these corners just sort of turning. So what this means is that you got the Gulf Stream in the wrong place, so you're going to get this bias. In climate models, you have this bit more shifted the North Atlantic Current, more to the east, and so you've got this fresh and cold subpolar water that gets into this area a bit differently than you otherwise would expect in observations. So really, this is an ocean model issue. This is not a coupled climate model issue. This comes from the ocean. And it's not just one issue. This is interrelated with a bunch of other things going on in ocean models. As one example, colder and fresher northwest corner biases are related to AMOC strength. So here on the x-axis, we got the northwest corner bias, and then the y-axis, we got AMOC strength at 45. This is an ocean-only OMIP models, and there's a very clear relationship, especially when you add all the cycles in. If you have a bigger bias, you're gonna have a weaker AMOC. So it'd be really great to reduce this bias in CMIP 7 models because this has downstream impacts on the atmosphere for North Atlantic atmospheric circulation and in Europe in teleconnections. So that's really the goal of our diagnostic suite, is to help developers point what kind of processes might be going on in this region to try and improve it on the fly. So features of the package that we hope to get in soon, hopefully this summer, is we're going to be really leveraging the OMIP simulations to give a quick look at how is your model doing relative to what CMIP 6 OMIP simulations were. There will be an AMOC and density coordinate tool that will show you what AMOC looks like in density coordinates. There will be the observational benchmarks for water mass transformation that Tadra just presented, which are particularly ideal for comparing to OMIP. And then we're going to connect some of those biases to water mass transformation. So in the time remaining, I'm going to kind of quickly go through what some of this is going to look like. Again, with the Casper outage last week, these are not the figures that I had hoped to have, but I've got it all mocked up anyway. So feature one, this is what Brendan Myers and Steve Yeager have been working on, particularly over the last about half a year. And so this is comparing an underdevelopment run to the suite of OMIP simulations. So we've got here on the left is the bias in upper ocean 200-meter temperature. This is in a development run provided very generously by Gustavo Marquez. I have no idea what run it is, but this is just for us getting the diagnostic right. So this is the bias. You can see that the two features I pointed out before, so the Gulf Stream bias in that warm area, so the Gulf Stream detaching too far north, and then the wrong turns of the North Atlantic Current are present. But the cool special sauce that Steve and Brendan have worked hard on is ranking these errors relative to the OMIP suite. So this is taking the absolute magnitude of the bias and comparing it against the same thing from each of the OMIP models. So in red, that would indicate the worst model. So this is saying that our in development run CSM3 in these regions is more biased than anything in all the OMIP models. In the, here's the 50th percentile. That's saying that CSM3 is falling, right in the middle. And then in blue, it says CSM3 is the least biased. So this is a quick look at saying, where is our simulation doing in comparison to other ones. And Steve and Brendan have put together a ton of other fields for this that are related to North Atlantic processes. So here, for example, is salinity. Again, you see those kind of the salinity and temperature and biases are going hand in hand, fresh and cool with warm and salty. And we've also got the bias rank similarly. Another feature that will be in the package is looking at where the biases in your model fall within the OMIP spread. So here, in yellow, is this underdevelopment run, and then we've got the temperature bias on the x-axis and the salinity bias on the y-axis. So even though it looks like it has some pretty big biases, it's actually in the middle of the pack, and that is because the temperature and salinity biases largely compensate. This is density now. So the density biases are weaker than the individual temperature and salinity biases, and that means that when we're looking in the OMIB model ranked space, CESM3 isn't as bad as most of it's actually on the better side compared to the OMIB models. Of course, you've got compensating errors going on here. If you have temperature that's not doing so hot, that's going to impact surface heat fluxes in certain ways that may not be ideal. But hopefully the combination of these figures together will give you, the developers, a quick idea of what's going on. So feature 2, over the last couple of years, I've been translating the CESM2 AMOC and density coordinate code from stuff that Steve Yeager had worked on and others have worked on here for years into something that can be more model agnostic and applied to any CMIP model. So this here, I've got a test model. It's not CESM, and I'm not going to tell you which model it is. So on the left, we've got AMOC in sigma coordinates. So this way is the direction you want to think as you're densifying down. So this is a random test model, and then on the right, I've got the OMIB multi-model mean. So a few things you can tell really quickly from this package, from this figure, is that this test model is a lot weaker, and its deep western boundary current, so down here, is occurring at a much lighter density class than in the multi-model mean. And those two things are linked. When you have a deep western boundary current that is occurring at denser classes, you tend to have a stronger AMOC. So these two things are going together. I've highlighted a couple of places that are of particular interest for this package, just for this talk. So the northwest corner exists in these latitude bounds in green, and then in blue is a particular area of interest because that's where you see the most OMIB spread in where the AMOC is on each density class. So those are areas of particular interest. So this is courtesy of Tedra Low. Now that we have AMOC, we know that surface buoyancy forcing largely balances, not entirely, but largely balances the AMOC in the North Atlantic. So this is part of that you'll see. So the black line is AMOC at 45. The red is the heat transport part. And you can kind of, so if you're comparing, not the heat, sorry, we want to compare purple and red. So purple is the total water mass transformation, black is the AMOC. Largely the same, they're not identical. Where they're not identical, it gives you a measure of where interior mixing is actually important. And one thing Tedra did not show is that CESM implies less of a role for water mass transformation in interior mixing than other OMIB models. Then you can also break down water mass transformation to surface heat fluxes versus freshwater to get a sense of how much those are contributing. And then you already saw a version of this from Tedra, so you can then break down water mass transformation throughout the total subpolar North Atlantic over here on the left into the different regions to get a sense of where you should be looking at the other processes. So North Atlantic current, then the subpolar gyre, Nordic seas, Erminger, and Labrador seas. So grade shaded region is again those observational benchmarks built from core and JRA forcing with OISST, HAD ISST, EN4 at ISHI. And then the different colored lines are different CESM2 simulations. High res and low res, you can see high res here in this dashed blue is actually doing pretty well compared to the two low res here in black and red. So a quick snapshot of, are you getting at least regional versions pretty well? So this is where we try to connect everything back together. So how do we connect water mass transformation in this kind of bulk basin-wide sense and AMOC in a basin-wide sense to what's going on in various specific locations? So what we've got here is this blue test model that I showed before for AMOC. And this is water mass transformation, also very, very weak, particularly when you stick on here, we've got this observational benchmark from Tedra. You can see that this model is very weak, and automatically you can tell, okay, this must mean that the density fluxes, in particular probably the surface heat fluxes, are way too weak. In another model, though, the surface heat fluxes might be okay, and instead what might be the issue is the isopycnal outcrops. So that's what we've got here in the next two panels. So observations here, these are observational benchmarks. In the yellow-red shading is you take the water mass transformation and you break it down into where exactly it's occurring. And then the blue shows you the frequency of occurrence of a specific outcrop at that time. So this is 36.6 sigma 2, corresponds to right here on the purple line. And so it's showing you that most of the transformation that's occurring for this blue line is occurring in observations at least, in the Erminger, a little bit in the Lab Sea, also up here in the Nordic seas. But in this test model, you can see you don't actually have those isopycnals available, and you only have transformation occurring up here. So this would suggest that you should start looking at what's causing the density biases. So go back to the figures we started with. How much density bias do we have up there? And then figuring out, is it coming for temperature or salinity, and building it back that way. So in summary, this is a quick mock-up of something that we plan to get into the NOAA Model Diagnostic Task Force in the next couple of months, and hopefully right after that we'll get into CUPID also, so that it will aid in CESM3 development. It features a lot of leveraging of the OMIP suite to kind of give you a sense of how you're doing compared to the past ocean-only models. It'll have the AMOC sigma calculation in it that's model agnostic, as well as a lot of water mass transformation decompositions and observational benchmarks that gives you some sense of how you're doing. And before I conclude, I want to bring one update from the NOAA Model Diagnostics Task Force about something that we're working on, which is Jupyter Notebooks. So something we've talked about a lot is how, everyone in this room pretty much is doing model diagnostics of one piece of another. But this doesn't necessarily end up into the packages that that go into the development. And so one thing that we're trying to think about is, everyone's got Jupyter Notebooks, and if we can streamline how we get those notebooks into packages like the MDTF, like CUPID, like GFDL's packages MAR, or like Australians, it makes maybe Jupyter Notebooks more plug and play into different, you can have the same diagnostic notebook going into multiple different frameworks at the same time. So in particular, Danny Coleman here at NCAR and John Crasting at GFDL are thinking, mocking up various notebooks to figure out how do you make kind of one interoperable notebook to plug and play into different packages. So I wanted to bring that to community attention to think about how do we get more of all of the work that all of us are doing into the model development, and maybe easy streamlined notebooks that are already plug and play for a bunch of different frameworks is a way forward. Thanks. Happy to take a few questions.
Questions for Liz?
Stuff. I was wondering, in the ranking plot that you showed, it seemed like there are a lot of fine scale features that maybe could be coming from models having dipole errors because you're not exactly representing the location of water masses or gyres exactly the right place. I was wondering if you'd considered some kind of model-specific diagnostics, for instance, using the model's own hydrography to define the subpolar gyre or something like that, as a bit more custom way of doing that.
That's a really cool idea. We hadn't quite considered that, but certainly that could be done.
Thanks.
I guess I'll add to that and say that OMIP simulations can be a bit of a bear to work with. So simple first, but I like the idea.
Questions? If not, let's thank Liz one more time. Our next speaker is Paul Hall. Hi, Paul, I see you're online. Welcome. And Paul will talk about theory waves in CSM3.
Hello, can everybody hear me?
Yes, we can hear you.
Yes, we can.
Great, fantastic. Welcome from rainy Providence. You have much better weather out there, I'm told. My name is Paul Hall. I'm a software engineer at Brown University, where I work with have been working with Baylor Fox Kemper to develop a theory waves module, which is sort of an empirical approximation of Langmuir mixing that can be used within CESM. And I'm here to provide an update on where that is. This is more of a development talk and less science. So for background, theory waves really started out, the theory wave story started out over a decade ago with the recognition that in global climate models, oftentimes you'd find that the mixed layer depth, especially in the Southern Ocean, was being underpredicted. So it was too shallow, as demonstrated here, in the, I don't know if you can see my pointer or not, but in panel B here with the control run, this is from Ching Li's 2017 paper, compared to the observations in panel A of the mixed layer depth in the Southern Ocean. Ching approached this problem by saying, well, let's look at the effect of Langmuir mixing on this and see if that explains part of the problem. So he developed a parameterization where he used an enhancement factor, Langmuir turbulence enhancement factor, that was derived from Stokes drift profiles from an empirical wave spectrum that was generated from WaveWatch 3, which he coupled into CESM. And in fact, using WaveWatch 3 to enhance Langmuir mixing or to account for Langmuir mixing did improve the ability of CESM to reproduce the mixed layer depth in the southern hemisphere, in the Southern Ocean. The difficulty with this, of course, is that WaveWatch 3 as a prognostic wave model is very computationally expensive. So then the question came about, is there a better way to do this? And Ching, working with Baylor and some others, developed theory waves, which is an analytical approximation of the Langmuir enhancement factor that comes from empirical wave spectra. So it's a very lightweight calculation, and it's based on empirical data. Ching developed this in his 2017 paper and actually implemented it within CESM within the CV mix package inside POP, the POP model at the time. And running theory waves in that context, this empirical simplification or simplified model of the Langmuir enhancement factor, as you can see in the panel labeled E over here on the right, yielded, again, is similar to WaveWatch 3, a much better mixed layer depth in the Southern Ocean than models that didn't have this sort of Langmuir enhancement in it. So the theory waves itself, the issue there, of course, is that the theory waves that he developed within POP or within CV mix is kind of hard to access. So what we've been trying to do is try to take theory waves out of CV mix, not actually take it out, but just make a second module or a standalone module of theory waves that we could then substitute in for WaveWatch 3 so that you could use this relatively lightweight calculation as a component within CESM in cases where you want to account for enhanced mixing in the upper layer of the ocean due to Langmuir mixing. So the idea is that this approximation that we're using, it's based on, again, the Langmuir spectrum, or the Langmuir enhancement factor, which comes from the Stokes drift profile, which is derived from a Phillips spectrum of the wave state, which means that it's WinC only, there's no swell, it's just local wave state. It's a beautifully simple model in that the inputs to it are just 10-meter wind speed, wind stress, and then the boundary layer thickness at a location, and then you get the enhancement factor out from that can be fed back into the wave model, or into the ocean model. This is just an overview of the sort of the equations, what we're actually solving in the theory waves module. And anyway, our immediate goal over the last several months has been to implement theory waves as a component within CESM as a low-cost alternative to WaveWatch 3. And again, the idea is that it would be useful in cases where you want to account for Langmuir mixing, but you don't want to take on the computational expense of a full prognostic wave model like WaveWatch 3. It is not a complete replacement for WaveWatch 3 in any way, shape, or form, but it does give you the Langmuir mixing ideally at very little cost, additional cost. Our approach has been to develop this as a drop-in replacement for the WaveWatch 3 component in CESM. And to do this, what we've actually done is we went to the WaveWatch 3, we actually just took WaveWatch 3 starting from the Dev Unified 0.0.13 tag and used it, sort of hollowed it out and plugged in the theory waves module to the WaveWatch 3 equation, short-circuited the WaveWatch wave model equations, the main solver, and replaced it with the theory waves approximation. To use this then, it's great because we can just drop it in directly for WaveWatch 3. We don't need to do make any changes in terms of having designated comp sets or anything like that. Anytime you run WaveWatch 3, you could just substitute in theory waves by pointing to the theory waves interface repo URL in the CESM.git module file. That's how we've implemented it right now. And we're using this whole idea of using the theory waves as the shell. It saves us time in development because we can use the existing nuopsy cap, and all of the existing I/O functions of WaveWatch, that also ensures a certain amount of consistency between the different wave models. So we have the same outputs coming out. So anything that any variables that you're expecting will come out from 30 waves that would normally be coming out from WaveWatch 3. The difference there, the main difference there is that there are a number of parameters that aren't solved for in 30 waves, in which case we're just passing out empty values or fill values. The wave elevation spectrum, for instance, which is a big part of the computational expense of WaveWatch 3. We aren't outputting right now. The other difference is that we did have to modify the nuopsy cap a little bit just to bring in wind stress from the atmosphere to calculate the Langmuir, to calculate Stokes drift and the Langmuir enhancement factor. Whereas WaveWatch, that's done internally, it calculates its own from just the wind speeds instead of the wind stresses. So it's a simple replacement, and we've been able to test it out now within CESM 3, thanks to help from Gustavo. We've actually run a test case now with CESM 3 and the Alpha 06B tag. The comp set, it's MOM6 plus the wave model, in this case theory waves, and data atmosphere with JRA forcing. We're using the E factor, which is the enhancement factor, the Langmuir enhancement factor wave method to incorporate the Langmuir enhancement factor and its effects into the ocean model. And we're using the VR12 method for your vertical turbulence within that. The run, in this case, we're doing 20-year runs, and I've done a case with WaveWatch and a case with theory waves just to get a comparison to show that we are, in fact, reproducing relatively well for the purposes of enhanced Langmuir mixing what WaveWatch 3 would give you with our theory waves approach. So I apologize for the not great quality of the maps. I went easy on this. So the model up top, this is just the final month of the run, monthly average at the end of the 20-year run, for sake of comparison between the case with WaveWatch 3 at the top, theory waves on the bottom. These are the predicted Langmuir multipliers. You can see that overall the patterns are relatively good. Consistent, same ballpark at least. The theory waves model does not have, it misses out on some of the peaks of the Langmuir multipliers. And it also loses, and this is by design, it actually has to do with the formulation of the Langmuir multiplier within theory waves. It can't have values of the Langmuir multiplier less than 1. So theory waves will only enhance mixing. It can't actually diminish the mixing, whereas if you're using WaveWatch 3, you will get some diminishment in the mixing or attenuation of mixing under the right set of circumstances. And you can see that in the dark blue colors here in the WaveWatch that aren't WaveWatch output that aren't reproduced entirely in the don't quite get that dark in the theory waves model. Comparing a little more directly, or you can see here, this is just taking the wind speed versus the Langmuir multiplier from the model that's generated by WaveWatch 3 versus theory waves. And as I said, in theory waves, you can see very clearly here that you don't have values less than 1 for the Langmuir multiplier. And again, that's by design. That's just the nature of the algorithm. Whereas in WaveWatch, you do get those values that are less than 1, where you will actually reduce the amount of mixing as a result of this Langmuir enhancement factor. It attenuates it. But that's in a small minority of cases. And doing more of a comparison here, this is a scatter plot of the two, where we've got WaveWatch 3 across the output of the Langmuir multiplier for WaveWatch 3 across the x-axis. The vertical axis, we've got theory waves. The red line shows what would be a 1-to-1 correlation. The gray plots, the gray dots is the scatter plot of all the values, and then the contours are just densities, with the outermost one being the 20%. So and maxing out at 90% with the yellow contour in the middle. So you can see that for the most part, it does a reasonably good job of reproducing the basic trends in the Langmuir multiplier. So theory waves is reproducing, it's in the ballpark with what you would get with WaveWatch. in terms of the mixed layer depth that comes out of this, and again, I apologize, the maps are not the best, you can't see the continents, but you can see that the overall pattern of the mixed layer depth that results from the two different approaches is very similar, and you plot them up as a scatter plot, and you can see they're pretty correlated with a one-to-one correlation. So we're actually producing an appropriate deepening of mixing of the mixed layer with the theory waves approach. In addition to those, we actually can also, through theory waves, generate some wave statistics from metrics that, again, WaveWatch 3 generates internally in a more vigorous or rigorous way. What we're doing here is we're using approximations for, in this case, significant wave height, assuming a Pearson-Moskowitz spectrum instead of the Phillips spectrum as the source here. And you can see it's just something. It's not meant to be an exact comparison because it's not quite apples to apples when you do this. But it shows that even if in terms of producing these metrics like significant wave height, was it peak frequency, mean frequency, things like that. If you can within theory waves get the output that you are getting. In terms of metrics out of the WaveWatch 3 model itself. And these are all output to the history files for the wave component. So in conclusion then, I just want to say that theory waves reproduces, we've demonstrated we have it as a standalone module now that we can replace WaveWatch with, and you get the same patterns for the Langer, or similar patterns, general patterns for the Langer multiplier and the boundary layer depth. With theory waves that you see with WaveWatch. Theory wave provides faster performance than WaveWatch 3. Just doing the simple swap out that we did of the main wave algorithm led to a 41% decrease in the wave component runtime. So for this particular model, at least for this particular case. And this is very simple. We expect to be able to get much more significant improvements with refactoring. Right now, we have a lot of overhead running the model for, again, because we used the WaveWatch 3 component as a starting point. There are a lot of routines that are being used right now, a lot of code that's being run that doesn't need to run because we're not using it for the theory waves approximation. But we started with just, okay, let's swap out the guts and the main wave model routine and see what we get. But without any further tinkering with the actual numerical values that we'll be getting out, without the actual solutions that we'd be getting, we could just, by removing unnecessary routines, we expect we'll be able to trim this time down even more significantly. Looking ahead to the future, we hope to be able to interchange this with WaveWatch 3, but also with Pickles, which is another wave model that's in development right now with Mo Mahel. We've been working with him on that, and with Brandon Reichel to sort of standardize the outputs between the three different wave models. And then going forward, I'm happy to answer questions, but actually I have a question for you, and maybe more particularly for Gustavo and Alper and others in the room who are on the development side, is that how should we go forward moving from here? How is it best to make something like theory waves available for the community to use? Right now it's as simple as just substituting a URL in the Git module file within the CESM sandbox that you're using, and which saves on the necessity of making separate comp sets or anything like that. So it's completely interchangeable. But I'm not sure that that's necessarily the best approach, and I'd be curious to know what you think. Thank you.
Would you answer the question, Gokhan?
Going to answer the question, but I guess it's a glass is half full of half empty thing, right? The plots that you showed, comparison of the WaveWatch 3, the full system versus the theory one, it depends upon interpretation. It may be really bad or it may be really good, and the gross features are similar. However, the boundary layer plot that you showed, they looked similar to the extent that it's pretty much this one. So can I interpret that thing in your test case, whether you use WaveWatch 3 or theory wave model? waves do not really matter?
So, yes, except that if you were to compare this to a case with no waves, then you get significant differences. The difference between theory waves and WaveWatch is insignificant. The patterns are the same. It's if you don't account for waves at all that you get into trouble, and especially in the southern.
Right. I mean, the question is, in that case, the follow-up would be, there are so many differences between theory and WaveWatch in the results, yet this doesn't change. So why is that?
That's a very good question. You know, I think it goes back to and Baylor would be a better person to ask about this, or Ching, the details of the numerics. I am just on the implementation side, but I think it goes back to the formulation of theory waves. You can see that for the most part, you may have some differences that are small here in terms of the Langmuir multiplier as a function of wind speed, which is primarily what's driving this. But the cluster doesn't vary much, right? It's always between 1 and 2. It's a little bit more mixing than you would have without the waves. So it's a little bit of deepening. But you know, and where the differences arise, you know, it can be a little distracting seeing these values of the Langmuir multiplier lower than 1 that you get with WaveWatch that you don't get with theory waves, and the bigger spread that you get with WaveWatch, which is again related to the fact that WaveWatch, as I understand it, takes into account the C state in terms of developing the calculating the stress that then goes into calculating the Langmuir multiplier.
Question for how to bring this into CSM. Unless Alper has something to say, have you put some thinking into it? Otherwise, we can get back to you later, because this is the first time I'm being confronted with this question, so I don't have much.
Yeah, no, you can get back to me later. I'm just floating it out there. So, you know, we're at some level where we have this thing that we've demonstrated. And again, it's not anything new. It was, Ching had developed this within CVMix, but it's just very hard to access within CVMix as a user. And this sort of breaks it out and makes it more explicit for people to use. But yeah, we're open to.
But I'm just wondering, your current version. So if I didn't misunderstand, you implemented this within WaveWatch 3, or is it a separate code base?
So what we did was we started off with the WaveWatch 3 code base. I just cloned it and created my own repo from it, and used everything from WaveWatch in terms of interfacing. So we used the nuopsy cap, we used the output to the history files and all of that, so we didn't have to rewrite that. All we did was we short-circuited or bypassed the wave model itself at this stage. So the component of the code where you're calling, what is it, W3 wave mod, within WaveWatch, we've just replaced that with a call to theory waves. And so there's all this overhead associated with WaveWatch, the WaveWatch code, which is making it slow still, that we need to go in and trim out now that we have some sense that everything's working.
Got it. So again, we should probably take the technical details offline, but I suppose it'll be quite straightforward to add it as a alternative wave model into CESM. But I was also wondering, in terms of both scientific and technical maintenance and support, what do you envision? Like, let's say we added this into CESM 3. What next?
Mm-hmm.
How do we keep developing it? How do we support it? How do we answer inquiries from communities in terms of both science and technicalities?
That's an excellent question, and that's something that we would have to work out between ourselves. I suspect that right now the idea is that we continue to support theory waves itself from here, from our end, just like you would with other community models. But that's an excellent question.
We're running behind, but thank you so much again, Paul, and we'll be in touch. Let's thank Paul one more time.
Thank you.
our last speak before the discussion is Joshua Cope. I'll let you read your title because it's a little complicated.
Hi, my name is Josh Coop. I'm a postdoc at CU Boulder, and I'm going to be talking about something a little bit different, phytoplankton. So I'm going to be showing some relatively preliminary results on some stratospheric aerosol injection simulations, or SAI, and I'm going to be looking at how the ecosystem model and changing it from 3P1Z to 4P2Z might affect how ecosystems respond to SAI. So what is SAI? I've included the very long acronym here for you to read at your leisure. It's a lot of you may know already, but it's 10 simulation ensembles using CESM2 with Wacom 6 as the atmosphere, POP2 and marbled 3P1Z, so slightly older version than what's going to be the default. And sulfate aerosols are injected into the stratosphere at 21 kilometers. And the goal of these simulations is to keep global surface temperatures at 1.5 degrees Celsius above the pre-industrial mean. Meanwhile, CO2 continues to go up following the SSP2 4.5 emissions. So as CO2 radiative forcing goes up, aerosol forcing also has to go up, and there will be consequences to that. In order to achieve this goal, this controller algorithm was developed. So the aerosols are injected at a couple of different latitudes. So while we want global surface temperatures to stay at 1.5 degrees Celsius, we also want temperatures, the pole to temperature gradient to stay the same. We don't want the intertropical convergence zone to move too much. That could be problematic for the monsoons. So this controller algorithm will put different amount of aerosols at different latitudes to control both of these two things. And then finally, as I said before, this model used 3P1Z configuration. So there's no explicit calcifying phytoplankton. Despite increasing CO2 and ocean acidification, it's important to know how the marine organisms might be affected by their environment, and then how their environment would then be affected by them. So in order to bridge the gap between these old simulations with no explicit calcifying phytoplankton and our desire to know how they would respond, I ran a simulation, another ARISE ensemble. It's only one simulation, so I don't know if I can really call it an ensemble, but it has a 4P2Z configuration, so it has the explicit Cook-Lith force now. So they can update carbon, they can produce calcium carbonate, and they also, their shelf thickness can change as a function of aqueous CO2, which would theoretically affect how they would do out in the wild. And as a refresher, I've said 3P1Z and 4P2Z a couple of times, but I might as well reiterate what that means. The 3P1Z there's 3 phytoplankton, small phytoplankton, diatoms and diazotrophs, and then there's a grazer class, a zooplankton, that will eat all of them. For the 4P2Z, which is a little more complicated, it's essentially a 3P1Z with the coccolithophores. And then the zooplankton are a little more complicated. So the zooplankton are divided into 2 different size classes, and they can both graze on the phytoplankton, and then one of the zooplankton will eat the smaller zooplankton. And this is supposed to be a little bit better for controlling blooms. Some details about the simulation. They start in 2015, and at around 2035, we hit 1.5 degrees Celsius above the pre-industrial mean. So that's when the sulfate aerosols start to get injected into the stratosphere. And then the simulation runs until 2070. So let's take a look at the physical climate state. What's going on in these simulations? Did we accomplish our goal? The gray shading here on the plot is the ensemble spread for the 3P1Z simulations. So 1900 through to the current day is in gray, and the yellow shading, if you can see that. Yeah, the yellow shading is SSP2 4.5, the control run, and then the purple shading is our aerosol experiment. The red line is the one simulation that I ran with the new, with the 4P2Z, and you can see it it mostly falls within the 3P1Z ensembles, which is good. Adding coccolithophores didn't affect the physical climate too much. And then the purple line is my SAI experiment. So once again, it falls within the distribution. And as we can see, the purple shading is right around 1.5 degrees above reference. So this is 2-meter air temperature. So we've accomplished our goal. We've saved the world. Well, obviously, not really. We all know better than that. There's obviously going to be consequences if something like this were to actually be employed. And that's illustrated in this next plot of surface temperature. There are some unintended consequences, even just in sea surface temperatures. So what this plot on the left here is showing is the change in sea surface temperature for the last decade of the SAI experiment minus the decade before the SAI experiment. So this is the original 3P1Z. There's 10 ensemble members. And you can see SSP 245, there's warming everywhere. And then there's this warming hole in the North Atlantic, likely linked to the slowing down of AMOC. Under SAI, we've done a pretty good job at cooling down most of the Earth, but the equatorial Pacific, this ENZER region, is definitely one place that we can't seem to mitigate warming. Crochet extension region is also still quite warm, and we just can't get rid of this warming hole in the North Atlantic. And if anything, it's gotten worse and expanded. So one takeaway from this is that SAI isn't slowing down, or not slowing down, it's not stopping down the slowing down of the AMOC, which is an interesting result in and of itself. How is chemistry changing? So obviously we're increasing CO2 and the ocean has stopped warming. This is going to cause an increase in dissolved inorganic carbon, which is what's being shown here. So the black is the SSP2 4.5 simulation. This is just my one 4P2Z simulation, but the 3P1Z is still pretty similar. You could see a divergence as soon as SAI begins. The purple line quickly outpaces the black line, which is indicating a lot more uptake of carbon in the surface oceans, just because there's relative cooling in the SAI case compared to the SSP2 4.5 case. Interestingly, pH is a bit more complicated. Carbonate chemistry, the constants that determine this are also temperature sensitive. So it's interesting, pH actually doesn't show that much of a difference between the SAI case and the SSP2 4.5 case. But more than just pH matters for organisms. So we took a look at the saturation state of calcite as well as aragonite. So calcite is the mineral form of calcium carbonate relevant for the calcifying phytoplankton, the coccolithophores in the model. And then aragonite is relevant for corals. And as the CO2, as the ocean continues to uptake carbon in these simulations, we see a decline in the omega calcite, or the saturation state of calcite, which indicates that it is becoming more difficult to form shells, more energy is required for organisms to maintain their shells. And just like the DIC plot, the purple line, the SAI experiment diverges as soon as SAI begins, and the decline is accelerating a bit faster for both calcite and aragonite, indicating it would be more difficult for these organisms to maintain their shells and build new shells, which suggests that they'd be much thinner and more prone to predation. And moving on to the actual title of my talk, which was, is there a difference between 3P1Z and 4P2Z? Does it actually make a difference in things like omega aragonite for corals? And obviously, I only have one ensemble member, so take this with a grain of salt. The black line is my SSP2 4.5 simulation. I have red shading to show the ensemble spread for the original simulations, and this seems to suggest that there is a baseline difference between the new 4P2Z and the older 3P1Z, whether or not that's because the calcifying phytoplankton are having feedbacks on the climate system and causing omega aragonite to be a little bit higher. Not sure at this point yet, would like to have some ensemble simulations to do a more robust comparison of these. But if you take a look at the SAI simulation for both of these, the blue line starts to, by the end of the simulation in 2070, starts to fall into this purple envelope, which seems to indicate that the new 4P2Z is a little bit more sensitive to SAI. There's maybe a little bit more of a reduction in the saturation state of aragonite. So slight model difference, maybe this model suggests more of an impact on corals for SAI. Finally, moving on to the phytoplankton response. So the model simulates phytoplankton. This is a plot just to show you what the distribution of phytoplankton, net primary productivity, looks like in the 4P2Z model, just to get a sense for when I should, the next like 6 plots are percent plots. So this is what it actually looks like. These peaks in the Equatorial Pacific and the North Atlantic. And then in the 3P1Z simulations, it's really, the phytoplankton response is mostly driven by physical climate changes. So you can see in the high latitudes, there's a 20% plus increase in phytoplankton in the Arctic, as well as in the Southern Ocean during this same time period that I was looking at for the temperature plots. And this is almost entirely driven by sea ice reduction under SSP 4.5. I believe I have a plot of that. This is a plot showing annual mean sea ice area in the Southern Ocean. And under SSP 4.5, you could see this decline. Interestingly, under SAI, because sea ice is not declining as much and seemed to have stabilized quite a bit, we've removed these gains in phytoplankton under SAI. So pros and cons. Phytoplankton don't do as well under SAI, but there's more sea ice for other organisms. Another very notable thing is that this warming hole in the North Atlantic, whether or not it's real, where the AMOC is slowing down this much and causing this much cooling or not, it's definitely having an effect on phytoplankton through temperature limitation. It's quite cold, and they can't be as productive, which might have effects for fisheries. And then another thing to note is that there's this robust response in the Sargasso Sea in the 3P1Z simulation, and it won't pop up. I'll spoil it. It won't pop up in the 4P2Z simulations, which is interesting. And if we this is basically a summary of all the results I gave before. SAI causes a decline in the tropics in productivity and increases in some parts of the North Atlantic, but it is a bit of a mixed bag. In other places, like at the Equatorial Pacific, you don't see obvious benefits. And then moving on to the 4P2Z simulations, it's pretty much the same thing. Phytoplankton response almost looks exactly the same, where it's driven by these physical processes. It's a sea ice decline, and it's the North Atlantic warming hole that's obviously still present in the 4P2Z because the physics haven't changed, thankfully. That was a good thing that the physics didn't change. And then again, this is the response in the 4P2Z. And then finally, the coccolithophores. This is what isn't in the 3P1Z, and I can't compare to the 3P1Z because it's only in the 4P2Z. So interestingly, coccolithophores decline this is essentially showing most of the coccolithophore mass is in this great calcite belt region in the Southern Ocean. There seems to be a shift to the south for this species. So in a lot of the Southern Ocean, you see an increase there. The removal of sea ice allows for coccolithophores to thrive in the Southern Ocean, as well as in the Arctic under SSP 2.5. And under SAI, it's quite mixed. In some sectors, there's a decline from sea ice benefits, and then in other sectors, there's an increase in productivity under SAI. So for phytoplankton, it's mostly sea ice and physical attributes. For coccolithophores, it's a bit more complicated, and we think that it does have something to do with carbon availability, especially in the Pacific Ocean. And then finally, to kind of summarize everything that I said, the effect of SAI seems to be a decline at high latitudes, and that's mostly sea ice driven. And then in other mid latitudes and tropical regions, this is possibly because of temperature being high temperature limitations being relieved because it's cooler. And that's my summary of conclusions. You can read, and we'll take any questions.
missed it. What is the, how are you doing the SAI? Which latitude or which height?
So, is it possible to go to a hidden slide? I think it's 30 north, so I think there's 4 latitudes, if I remember. I think it's 30 north, 15 north, 15 south, 30 south.
It's all simultaneous injection?
Yes, it's the controller algorithm.
Okay. I mean, the reason I was asking is essentially that the response of the boundary layer depth or the cold blob and AMOC is strongly dependent upon which latitude you impose the SAI. There's nothing impacting those if they're imposed south of the equator, including the equator. If you do the 15-degree, 30-degree, 45-degree injections, then you get the same impact that you are showing. So there is a strong latitudinal dependence of the strength. But anyway, we can discuss it. We have a paper on it. I can send it to you.
Yeah, I think we were using the 30, 15, 15, 30 controller, but we can talk later.
You know, there's more questions. Can you guys connect offline? We are out of time and need to move to discussion. Let's thank Josh one more time.
I don't have any other slides for
No,
this
there's
session.
no number 9.
Let me check the folder. Okay, I'm downloading your slides now.
Thank you. Okay, so for the discussion, Ian and I put together a few slides, and also we hope to leave some time for open discussion. So based on what we heard yesterday morning from Dave Lawrence, Lab C was freezing, like he did not mention explicitly, but one thing that we did in the latest runs, we suppressed the submeso scale mixing only within the Labrador Sea, and that so far, fingers crossed, seemed to have helped with the Lab C freezing, and that in this time series of minimum SST in the Labrador Sea is the red line, the red time series that has gone now for over 100 years and still has not frozen. You can see the 2 black lines, the solid and dashed, are examples of cases that have frozen. So it seems like this will be, so far it's looking promising. We do have another option, which is in addition of shutting off submeso scale, we can also shut off the near surface ready component. We call it horizontal boundary diffusion. That is another possibility as well, but seems like with only suppressing submeso, we will be fine. Again, TBD. Another things that we have, another issue that we have been dealing with, which most people here will not care about, is if you go and download Beta 06, our latest sandbox, and you run a case, you will get some truncation errors. It's not in many, it's only a few locations, usually when you have steep slopes and then a thick cell next to a bigger cell in thickness. And to suppress that, we have enabled the Smagorinsky-Laplacian viscosity, and that seems to have solved the problem. So here's a time series of that, how many truncations we have. Is only a 20-year run, and there's 0. And on the right, this is just from at the end of the run, a monthly mean of how the Laplacian viscosity looks like in a map. And the large values tend to occur near the boundaries. That's how this scheme was designed to do this kind of thing. It doesn't affect the key metrics if you do a case with and without the SMAG, allowing truncations to occur like the key metrics don't change. So again, this is only for the purpose of get rid of truncation errors. We have also been playing with boundary layer schemes, like 2 different schemes, as well as the setting in KPP. So this is, we were close to putting together KPP, the new version of KPP that Biology is working on. And then I did a sensitivity run where I replaced all the vertical mixing from NCARD with GFGL's version of that, just to see what would happen. And it turned out that it improved some of the key biases that we have. One of each is the sea ice, Southern Hemisphere sea ice area, which is shown on the top left. And the run in blue, this is the out of the box. And we are comparing against the black line, which is the observational based. And then when we switch to PBL, the GFGL's vertical mixing scheme, that's the running in red, we got much better agreement with OBS. And that is because if you now look at the 2 panels on the top right, the 2 maps, that's KPP versus PBL, this is showing the SST bias, the run minus a baseline run, which is the run 170 in this case. And the purple line in these plots represent the ice edge, the sea ice edge. You can see on the top right panel that with EPBL, you get this warm bias, which is what's causing the sea ice to melt, and therefore getting us closer to OBS. And these are all fully coupled runs. In addition to improving the sea ice extent in the Southern Ocean, Southern Hemisphere rather, the switching to EPBL also improved this thermocline biases that we see in the tropical regions. I'm highlighting these regions on the bottom panel, the 2 bottom panels on the right. And KPP on the left, EPBL on the right. And if you look closely, it's improved with EPBL. And although we don't know for sure, we think that these thermocline biases might have some implication for ENSO representation. So because of that, now Bill Lodge has been working on an energetics-based version of KPP, which when he incorporated waves into KPP, that was the original plan. So if you go in and look at his paper, I think it's 2023, that's what's in there. But we had not implemented in CVMix yet. So that's happening now. In conjunction with evaluating this new KPP, we will also evaluate the KPP plus the LF17. So that's the scheme that Paul Hall was talking about that was using CSM2 with the enhanced wave mixing on top of KPP. So these are our next steps for hopefully getting something close to what we get with EPBL. Moving on now, I borrowed this slide from, again, Dave's presentation on Monday. So this is some of the improvements that we are seeing in the equatorial ocean when we add kinetic energy backscatter. So that's the same plot that Dave showed. So those are transects of zonal velocity. Top left is OBS, top right is POP, bottom left is MOM without backscatter, bottom right is MOM with the kinetic energy backscatter. And we see that adding the kinetic energy backscatter leads to the emergence of the so-called Tsuchiya jets. We don't see them in POP, we don't see them in MOM without backscatter, and they are present in OBS. We don't show here, but we run cases with BGC and backscatter, and adding backscatter with BGC leads to a significant improvement in the bias of the oxygen minimum zones in the equator. So it's very promising. We would like to move forward with this. However, adding backscatter also seems like to impact negatively the Meridional overturning circulation, and this is the global one shown on the bottom right. And if you look in the equator at depth, you see something that it looks weird. And looking at the velocities at depth, you see these pulses of high velocities coming in. So we have ideas on how to keep the near surface properties or effects of backscatter, which will lead to the improvements such as Tsuchiya jets and consequent improvements in BGC, while getting rid of what happens at depth and deteriorates MOC. So again, those are we have 2 ideas, and we'll move forward with them and hopefully can maintain the benefits of the energy backscatter. And then finally is the choice of the target densities and thicknesses for the HiCom1 coordinate. So we have been using, again, out-of-the-box settings is a convoluted way that we combine the vertical grid that GFGL was using with what the FSU Navy people were using with MOM6 and HiCom1 vertical coordinate, plus some tweaks that we did it to get rid of thick layers. So it was a very convoluted way to come up with those targets. In the meantime, then, Ian developed a new method for specifying these target densities given an initial GNS state. And this new method is looking very promising. We've done forced simulations, we've done fully coupled simulations, and also Jean from the Paleoclimate Working Group has done LGM simulations. So we're pretty confident that it's working together, although we need to do some further analysis to check that box. But if everything goes well, and if at least we get as good as a representation using the new method, we would like to move forward with that because, one, it can be reproducible, and two, we can apply the same method for other scenarios. And I think that's all I had here, and we can have some discussions if people want to ask any questions about these or any other topics. We're happy to answer the questions.
Since we're already a few minutes into the break, I don't want to keep you too long. If there's anybody from NCAR Ocean section here, maybe you guys could save discussion until later because we can talk anytime. But if anybody not local, but who's here and has something to say, we would welcome that. Otherwise, we could just go to break.
I was just about the Bodner, about the submeso restrictions in the Lab C. Are you using the Bodner scheme, the new one?
Yes.
And okay, so you've answered the question then. Okay, so I mean, is there any way to try and actually change the length scale rather than just turn it off? Is there a contour of kind of threshold contour you can change to kind of that encapsulates the Labrador Sea? So you haven't got this kind of geographic mask. No.
No, one way of we thought that since it's a region where you have deep boundary depths, we could potentially modify Bodner itself to turn it off once you have deep convection. But so far you're using a mask in the efficiency coefficient of Bodner.
All right, in the absence of further questions, let's once more thank all the speakers and then go to break.